In this lecture, we'll be looking at the set of real numbers. So the set of real numbers has a special symbol associated to it. So how we called sets A, and we said, there was some numbers in there. That's cool. There's some numbers in A. Great. For the real numbers, we have a special name for it, or a symbol, and it's basically like a bolded capital R. It looks like this. So that's the set of real numbers. So a great way to think of or visualize a set of real numbers is just a number line. So if we draw a number line, we'll put 0 in the middle, 1, 2, and 3, and negatives. Remember, the real numbers are just any number that's not complex. Like, that's kind of really the entire idea. So it's not just including these numbers, it's everything in between all these numbers. So, we can have, square root of 2, we can have e, we can have pi, we can have fractions too, right? We can have negative 1/2, right? We can have negative e, right? That's the idea, okay? Real numbers are practically just your number line, 0, 1, 2, 3, all the way out to infinity on both sides, and everything in between. That's the entirety of real numbers, and it's denoted by this bolded looking R. Now let's discuss some subsets. Remember, subsets are sets that are contained in a larger set. So some subsets of the real numbers, we'll look at a table. So we have the natural numbers. We also have integers. And we also have rational numbers. And you can think of those as fractions. And we'll just make a little table. So this is, we'll call a subset. And the notation there's notation for each set. So when we talk about the natural numbers, right? The natural numbers are just your positive counting numbers, starting at 1. So 1, 2, 3, 4, 5, all the way out. And we denote the natural numbers with a bolded capital N. Something like that. And the integers are denoted with a bolded capital Z. And the integers are, and I'll actually write as well, kind of scooch it over here a little bit, some elements. So some elements of our natural numbers are just our positive counting numbers, starting at 1. So it's just 1, 2, 3, 4, all the way out to positive infinity. 0 is not in the natural numbers. We'll be using that convention. And there are no negatives or fractions, just your positive counting numbers. That is it. Integers are all of the positive and negative natural numbers, including 0. So we can write it out something like, this. So those are your positive and negative counting numbers, including 0. Those are your integers. So you can think of that as just the number line with nothing in between, just those discrete values. In the rational numbers, we'll be using this one quite a bit too. We denote this with a capital Q with a little bolded piece. And these elements will include, anything right? 0, 1, 2, -1, as well as fractions. So, 1/2, 3/4. Let me just keep going, right? Any fraction you can think of, positive or negative. And specifically, we can actually define the rational numbers as a set, and we'll do that. So the set Q is equal to little p over little q such that p and q are integers. So remember, if they're integers, that means they're elements of the integers, which we call capital Z. And we can write out and explicitly. You could also do like an intersection notation if you wanted to, if you're familiar with that. We also need to define Q is non-zero, right? Because we can't have a set of fractions where Q is 0, because Q is an integer, or 0 is an integer, right? So we need to explicitly say we can't divide by 0. So if you want to be very formal about it, we can use, and I'll delete this intersection, it's not really important. It's good to sometimes visualize this the rational numbers explicitly, as well as the integers and natural numbers. You could write them out as well. But we say that the rational numbers are all values, all numbers in the form p over q, such that p and q are members or elements of the integers, and q is non-zero. So we can just think of some examples, right? I mean, the rational numbers take up a very large chunk, right? So, right, if p, pick an integer, right? P and q. So we can say -7, that's an integer, and then q, 4. Those are both integers. So that is going to be in q, right? And we explicitly say that q can't be 0 because we can't divide by 0. That's it, right? So this is a very explicit way of defining the rational numbers. So it's all numbers in the form p over q such that p and q are elements of the integers, and q is non-zero. That's it. So we should be asking ourselves, okay, what's the difference between the real numbers and the rational numbers, right? Because it seems like you can get any number you want out of here. Almost. Remember, there are irrational numbers, right? So irrational numbers include e, pi, √2, just to name a few. These are all irrational numbers. So you cannot write e as a fraction of two integers, right? There are no two integers, p and q, that can be written as e. This is not and this is a proof that we can do. We'll actually do one later with the square root of 2, proving that it's irrational. So the real numbers contain rational numbers and irrational numbers, right? And we're not ever going to work with a set of irrational numbers, right? We'll just be working with rational numbers. So we can say that the natural numbers will I'll delete. Actually, I'll just move up here now. Scooch it over a bit. So the natural numbers, that is a subset of the integers. And that is also a subset of the rational numbers, which is a subset of the real numbers. So there's kind of a logical order to it. So if we just think of like our basic counting numbers, all of those counting numbers, 1, 2, 3, 4, all the way out to infinity are inside of the integers, right? Because the integers is all the counting numbers, including their negatives and zeros. And we can keep going further, right? All integers are inside of the rational numbers, because the rational numbers are all integers p over q, where q is non-zero, right? And any integer can be written as a fraction p over q of other integers, right? So, the integers are things like, 2, I can write that as 4 over 2, right? 4 and 2 are integers. So, so we can say that, right? And that's just one example. And then finally, all of these things, right, are members of the real numbers. So, and that includes irrational numbers, but we're not going to be using a set to denote irrational numbers, right? I'll get rid of this. And I guess what you could do if you really wanted to, there's a thing called, we could do the difference of a set, right? So you could say that, I'm not personally familiar if there is notation for irrational numbers, but we could say that the irrational numbers are just the real numbers minus the rational numbers, right? Basically what's left over. And these would be irrational. So there's a set difference, right? Basically this says take every element in the real numbers and remove all elements that are in the set of rational numbers, and you're left with just the irrational numbers. So that's what a set difference is. We'll be using that a little bit, but that's if you really want to do that. So just to reiterate, we discussed the set of real numbers denoted as a bolded capital R, and we can visualize that on a number line, and that is going to include every number on the number line and in between all the numbers. And there are subsets of the real numbers. We have the natural numbers, we have the integers, and we have the rational numbers. Natural numbers are just your positive counting numbers. Integers are just your positive and negative counting numbers that include 0. And the rational numbers are all numbers in the form p over q, where p and q are integers, and of course q is non-zero. And there are irrational numbers, right? So that's kind of what makes the difference between rational numbers and the real numbers. So the real numbers include e, pi, root 2. The rational numbers do not include those values. So we could say, right, that the square root of 2 is not an element of q. And this should be a not equal, right? There's no way we can get p and q that are integers written as a fraction to equal e. Impossible. And there is a natural order to these. So there's a reason I put them in this order specifically. It's because they're all subsets of each other. The natural numbers are a subset of the integers. The integers are a subset of the rational numbers, and the rational numbers are a subset of the real numbers. So that will conclude just the real numbers as well as their subsets. These will be very important and used in the later lessons. So next time we'll just be looking at some basic arithmetic and inequalities.